All right. Well, hello everybody. Welcome to this glorious Tuesday. Hope you have your earbuds in because otherwise you're going to be hearing everybody else's. So, what we're working with today is vectors, and remember that a vector is representing anything that has a magnitude and a direction. So, a couple of examples of vectors would include displacement, and velocity, and acceleration, and force, which all of these you'll be working with today. So really it's kind of imperative that you know that a vector is not just velocity, it's really anything that has a magnitude and a direction. So what we're going to do is we're going to go ahead and do an example problem. So the first thing you've got to do with any problem is always the same. You've got to read what's going on. So calculate the resultant velocity of an airplane that normally flies at 200 kilometers per hour if it encounters a 50 kilometer tailwind. Draw a vector diagram to represent this situation. So the key thing with any vector diagram is you really need to have a scale, and the scale is kind of whatever you want it to be. I'm not going to give you scales to work with. My recommendation is that you should be doing everything in centimeters, so I would say 1 centimeter is equal to whatever you're choosing is, and you probably want it to fit in the space that's given to you, so make your scale appropriately. In this case, because we have 200 kilometers and 50, I'm probably going to say that every 1 centimeter is going to be equal to 25 kilometers per hour, just to make it easier, because for me, I have a lot of space. For you, you might not have as much space, so you might want to do 1 centimeter is equal to 50 kilometers per hour. It's really up to you. Next is you need to have representation of what's going on, and of course the way that you represent a vector is with a vector arrow. So at this point you would want to draw your plane, and because they don't specifically tell you which direction it's going, I'm going to decide that we're going up. So it is, oh, by the way, you need one of these nice little things. So there should be rulers on your desk. If not, go ask the sub for them. She should have they should have a bag at the front up there. So in the first example, the plane is going 200 kilometers per hour. Now, if you are a person of skilled drawing habits, then you are more than welcome to go ahead and get out your awesome pin set and anything else that you want to. But in this case, I will be just using one single arrow. So I'm going to draw one arrow, and that arrow is going to be represent 200 kilometers per hour. So there's my representation for my plane. I'm also going to need a representation of undo that. A representation of what the actual wind is doing. So the tailwind, because it's 50 kilometers per hour. Gotta go way back. So taking it in, 200 kilometers per hour. 1 would mean that it needs to be 8 centimeters altogether. So there is 200 kilometers per hour. That's my representation for the actual plane. The tailwind is 50, so I'm going to go ahead and make it into 2 centimeters. So now I have a 50 kilometer per hour tailwind. And you show the display, so because it's a tailwind, it's going in the same direction. And one of the things we got from your notes is that all vectors that go in the same direction are going to add on top of each other. Now, the easiest way to show this is to actually do what I call a tip-to-tail method. So you're going to take the 200 kilometers per hour. You're actually going to draw the tailwind in the same direction starting at the tip from the other one. So we're going to redraw this arrow, this 50 kilometers per hour. We're actually going to take and we're going to translate so that it's tipped to tail on this guy. So we have another 2 centimeters here. So that's 50 kilometers per hour. And this shows us what our resultant velocity is going to be. So the resultant velocity in this case is 200 plus 50, which means our resultant vector should be 10 centimeters long, because it goes all the way from the bottom down here all the way to the top. So we're going to go ahead and draw that in. 10. And so our resultant, how fast would it be going all together? It'd be going a total of 250 kilometers per hour. And that would be your answer. So a couple of things. Number one, make sure that they are drawn to scale. So you need to make sure that they're in scale. Do the tip to tail method and then draw on your resultant over here on the side. Continuing on. Question B. So, calculate the resultant velocity if the same airplane encounters a 50 km per hour headwind. So, draw a vector diagram to represent the situation. So, again, we have the same plane. I'm going to use the same scale, so you're more than welcome to use the same scale if you want to. I said that for every 1 centimeter is going to be equal to 25 kilometers per hour. All right. So my plane is still going to be headed in the same direction, so I'm still going to draw him in the same direction. In this case, let's see, I've got 200 kilometers per hour. I'm going to have him going north, so his arrow is going to be 8 centimeters long, and I'm going to label him. He's still going 200 kilometers per hour. Fantastic. So there's my plane. I got to do the same thing. So now my wind is not coming, it's not a tailwind, it's now coming at me, it's a headwind. So it's still 50 kilometers per hour, but now it's headed in the opposite direction. So it's still 2 centimeters long, but now it's headed in the opposite direction. So it points in the opposite direction. Still label it. It is still 50 kilometers per hour. So we have those two. So you still represent them the same way, but now because they're in opposite directions, they're not going to add on top of each other. They're not going to take away from each other. So we still do the tip-to-tail method. So the easiest part is you're going to take the tail end of this and you're going to put it on the tip of this, and it's going to look like that guy. So notice that they overlap with each other, and what they mean by they're overlapping here is they're actually canceling out. So when we draw on our resultant vector, the resultant vector is still going to do the same thing. It's still going to start from where the arrows start, and it's going to end where they end. So in this case, you still lay it down on there. Your resultant's down here at the bottom, and it should go up to match the endpoint. And if you notice, it should be 6 centimeters long because the 200 was 8 centimeters, the 50 was 2 centimeters in the opposite direction. So altogether, your resultant vector should be 6 centimeters long, and that means that the plane was actually going 150 kilometers per hour. And because it's a vector, it has to have a direction, so this is going to be 150 kilometers per hour going north. So again, because the vectors are going in opposite directions, they're actually going to subtract from each other. So altogether, we have a resultant vector or a resultant velocity of 150 kilometers per hour going north, because we have to have our directional piece that goes along with it. Sweet. Letter C. So letter C says calculate the magnitude of the resultant of a pair of 100 kilometer per hour velocity vectors that are at right angles to each other, and draw a vector diagram that represents this situation. So they don't really specify direction on this one, but I'm going to go ahead and specify direction. So the way that I usually do it is I draw my little compass rose, and north is going to be up the page, south is going to be down the page, west will be to the left, and east will be to the right. So there's my little compass rose. Now they specify that we need to have 2 vectors. So in this case, we're going to have one vector that is going north at 100 kilometers per hour, and I'm going to set my scale. My scale is going to be for every 1 centimeter is going to be equal to, let's do 25 kilometers per hour. So if it's 100 kilometers per hour, 100 divided by 25 comes out to be the fantastic number of 4. So we're going to draw him in there. So 4 centimeters up, because we said that the first guy is going north. I'm going to label him. He's going to be 100 kilometers per hour north. The second one, so the second one that we're going to draw is going to still be 100 kilometers per hour, but now I'm going to specify that he's going east. So he's at a right angle, so we're going to say that he's going east. He's still 4 centimeters long, but now that he's 4 centimeters long, he's 4 centimeters long going east. So we draw him in, 1, 2, 3, 4. Draw an arrowhead. Again, you have to label him. So he's going to be 100 kilometers per hour going east. So we have our 2 vectors. We've got one guy, complete right angle to that should be this guy. Making sure that I've got, nope, these. Okay, so you still do the same thing. It's going to be tip to tail on it. So we're going to take one of the tips and put it on the tail. And it doesn't really matter which way you do it, because if we do it this way, or if we do it this way, it ends up the same way. So we're going to do it, let's do it this way. Okay, so having those 2 tip to tail, which is really important, having the tip to the tail of another one, is now we can draw on our resultant vector, and the same thing still applies. You're still going to start where the arrows start, and you're going to finish where the arrows finish. So in this case, if we drew our resultant vector, he's not going to be perfectly in a straight line. Well, he's going to be in a straight line. I guess he's not going to be perpendicular to the others. So there he is, and all of a sudden we have a triangle. So if we label this blue one now, this blue one is our resultant. It's when you combine these two, but we're actually going to have to bring them all together. So if you notice, what we've made is we've made a triangle. So this would be side A, side B, and what we're solving for is we're actually solving for side C. So this takes us straight to Pythagorean theorem, which means we're going to do A squared plus B squared is equal to C squared. So filling in the blanks here, 100 squared plus 100 squared is equal to C squared. 100 squared is actually 10,000 plus 10,000 is equal to C squared. So 20,000 is equal to C squared. Now we don't want C squared, we want C. So the way to get C by itself over here, we have to take the square root. So the square root on the right. If we take the square root on the right, we have to take the square root on the left, which means we need to find the square root of C. So you go put it into your handy dandy calculator, which I'm doing right now. I think you should do the same. Calculator. Flip to the side. 20,000 square root equals 141. So C would be equal to 141. I'm going to consider having 3 sig figs, so it's still 141. 141 what? Kilometers per hour, and we have to specify a direction. So this guy's not just headed north, he's not just headed east, he's headed northeast. So we would say 141 kilometers per hour going northeast, and that would actually be what it was. So in terms of of measuring this guy, we could put our ruler up there, and if you measured your ruler, he comes out to be about 5.5 centimeters. 5.5 times 25 is about 137.5. So diagram wise we're pretty close, but this would really be more accurate with the actual equation that goes along with it. Alright, so there's 3 examples. Now your job for the rest of it is you're going to do 1 through, let's see, there are 6 of them. So you've got 1 through 6 on your own. You need to show your vectors, so you actually have to draw a diagram for each one of them. The sub does have a key. Now, they are not going to give you the answers, but if you would like to go up there and say, well, what is the answer, and if you'd like to say, hey, this is my answer, did I get it right, maybe they can help you out that way. Please be good. If you would like to work with your headphones in, you're more than welcome to do that. Stay working. Oh, by the way, when is this due? This is going to be due when I come back on Friday. So you will not hand this into the sub. You will turn this into me. Thank you. Have a good day. Don't mess my room up.